Now, let us do the next problem. Start from the next problem. Here, what we are discussing was dehumidification and humidification process. Now, we have a problem. We have a sums here. The atmospheric air at 30-degree dry bulb temperature and 75-degree relative humidity enters a cooling coil at the rate of 200 meter cube per minute. Now, the coil dew point temperature is 14 degrees centigrade and bypass temperature of the coil is around bypass factor of the coil is around 0.1. So we are supposed to determine the temperature of the air leaving the cooling coil, the capacity of the cooling coil in terms of refrigeration and in kilowatt, the amount of water vapor removed per minute, and 4, the sensible heat factor for the process. We know atmospheric air at 30-degree dry bulb temperature means when the chamber is dry and has a negligible moisture, its temperature is 30 degrees centigrade, and the relative 75% relative humidity means the amount of moisture present for a given volume of air as well as vapor mixture. And the ratio between the amount of moisture present in a given volume of air and air vapor mixture to the same volume of air vapor mixture when it is fully saturated means it is 75% of the full saturation, 75% of the amount of vapor of which is when it is fully saturated. Then the air enters a cooling coil at the rate of 200 cubic meter per minute. Means the rate of flow is mass rate of flow of air and vapor mixture is 200 meter cube per minute. The coil dew point temperature is 14 degrees centigrade. What is dew point temperature? When a mixture of air and air vapor is the partial pressure of the air vapor is such that air vapor reaches its fully saturation temperature as per its own partial vapor. The dew point temperature is the saturation temperature of the air vapor contains in the mixture as per the partial vapor of the vapor in this mixture. So at the fully saturation temperature means at 14 degrees centigrade that with the same partial vapor pressure of the air vapor air mixture, the dew point is fully saturated 14 degrees centigrade, which means if temperature is reduced further, it will start a condensation into droplets of the vapor. The bypass factor of the coil is 0.1 meter. 0.1 means the fact any air vapor passing through the coil cannot go through this temperature of the cannot come back to the temperature of the coil, but it remains at a temperature higher than the coil. So portion of the air is bypassing the coil. So the bypass factor of the coil is given as 0.1, and bypass factor is given by this equation. At bypass factor of the cold coil is given by the solution is TD3 minus TD2, where TD3 minus TD1 is the where temperature TD1 is the temperature of the cooling coil. Temperature incoming air, TD2 is temperature of the outgoing air, and TD3 is temperature of the bypass factor, bypass cooling coil. So let us see temperature leaving the condenser coil, which we are supposed to calculate. Now, TD1 we know 30 degrees centigrade, phi1 is known 75. Velocity of the air coming inside the device is 200 meter per meter cube, and bypass apparatus dew point factor is dew point temperature. Apparatus dew point temperature is given by the ADP. TD4 is equal to 14 degrees centigrade. The temperature of air leaving the cooling coil, let TD2 temperature of the leaving the cooling coil. First of all, mark the initial condition of the air. Let 30 degrees centigrade dipole temperature, 35 degrees centigrade, 25% relativity of the psychrometric chart at point 1. So here, first you have to mark it the psychrometric chart. The first initial condition of the air is 30 degrees centigrade trival temperature, which in the trival temperature line, we put the point 30 degree and 75%. Now, so what we do here, we are marking the 30 degrees centigrade on psychrometric chart on trival temperature, and we drop a particle from the point 30, which will intersect the relative humidity line at 75 degrees centigrade at the point 1, and the dew point temperature of the inner light of the entering air at point 1 will be, if we draw a horizontal, this is the and it will be the specific humidity of W1, means the amount of moisture present per kg of the dry air, per kg of the air vapor air mixture. That is point 1. And dew point temperature of the entering air will be given by 35 from the cell dew point temperature. If we drop a horizontal line which is set at the wet bulb temperature line, that is the dew point temperature at 35 degrees centigrade, that is 25 degrees centigrade of the wet bulb line. Since that coil dew point temperature or dP is less than the dew point temperature of the entering air, therefore it's a process of cooling at different temperature. We know that bypass factor, the TD2 minus TD4, TD1 minus TD4, where TD2 is the temperature of dipole temperature of the outgoing air, TB1 dipole temperature of the incoming air, TB4 type temperature or dew point temperature of the incoming coil. Now, that by bypass factor, TDP is given as we put TD4 as ATP apparatus dew point temperature, which is given as 14 degrees centigrade. The coil dew point temperature apparatus dew point is 14 degrees centigrade, so we put it here. So what we have the bypass factor, we have incoming air dipole temperature and apparatus dew point temperature, and thus we can calculate the temperature T2, the temperature at the outlet of the uh, outlet outlet temperature of the reactor gas, that is 15.6 degrees centigrade. Next, the capacity of the cooling coil. Next, we are supposed to calculate the capacity of the coil in tonnage of refrigerant and in kilowatt. Means how much we have to calculate how much heat can be removed by this type of cooling processes. When we know temperature of H1 and temperature H2. Now, the resulting condition of the air coming out of the coil is shown by the point 2. Here, aperture 3-point temperature and altitude particle and joint the point on the line, joint the point 1 and 4. 1 and 4. This aperture 3-point temperature, and if we make a tangent from here to here, which is given here, and it will intersect at the point 2. The line 1, 2 is present the cooling and humidification process, which is assumed to follow the line part 1 into A and A to 2. By part 2 A humidification, A to 2 is at cooling. Now for the psychrometric chart, we find that water vapor in the entering air or the specific humidity of entering air, specific humidity of the entering air at point 1 is given as 0.0220 kg per kg of dry air. Vapor of the air at leaving at the specific humidity of the leaving at point 2 is given as 0.011 kg per kg of dry air. The specific volume of entering air at point 1 is 0.88 kilometer, enthalpy of air at point 1 from the chart 82 kilojoule at point A, enthalpy at the outlet at the upper dew point is 48 kilojoule per kg, enthalpy of air dipping at point 2, the outlet of the air pressure is minus 2, that is H2 43.5 kilojoule per kg. So the mass of air flowing through the cooling coil is the volume of air coming in and divided by the specific volume of the air at the incoming temperature, that is 0.0884, and 200 kg is the incoming air is given. So 2 to 6.2 kg per minute is the mass of the air coming in. The capacity of the cooling coil in terms of refrigerator is the mass of the air which is coming in minus multiplied by the enthalpy of the incoming air minus enthalpy of the outgoing air. So 2 to 6.2 minus H1, which is given here, 82 kilojoule per kg, and H2, which is given as 43.5, 8709 kilojoule per kg, or divided by 210, 41.5 ton. Thus, the capacity of the cooling coil 8 kilowatt, 8709 divided by 60, it is means kilojoule per second, or 145.15 kilowatt. The amount of water vapor removed per minute is, note that the amount of water vapor removed is mass into mass of past flow of vapor multiplied by the specific humidity at the point 1 minus specific humidity at the point 2. This is the amount of water vapor reduced when we know the mass spread rate of vapor-air mixture, which is equal to 2 to 6.2. So we put the value of W1 at 0.0202 minus 0.0111 is equal, and make the multiplication, we will get 2.08 kilojoule per k minute. Sensible heat factor for the machine. Sensible heat factor is the apparatus enthalpy of the apparatus minus enthalpy of the outlet air divided by enthalpy of the incoming air minus enthalpy of the outgoing air. This 58 minus 43.5 divided by 82 minus 43.5 is equal to 0.377. A moisture enters the refrigeration coil at next question, next problem, 16, number 16. The moisture enters the refrigeration coil at 35 degrees centigrade dry bulb temperature and 55% relative humidity at the rate 100 cubic meter per minute. The barometric pressure is 1.013. The pair lives at 27 degrees centigrade. Means outgoing temperature and dry bulb temperature and incoming temperature, dry bulb temperature is given. Mass flow rate of volume flow rate is given, also given. We do, if you know the specific volume, we'll get the mass flow rate multiplied by, and relative humidity incoming air is 55% is given. So calculate the terms of refrigeration required and the terms of refrigeration required at the final relative humidity. So we need the final temperature, the incoming and final temperature is going up to need the capacity of the refrigeration and the final relative humidity. If the temperature, if the surface temperature of the cooling coil is 10 degrees centigrade, Poisson's factor is only 0.1, calculate the terms of the required at the concentrate 4. Now TD1 35, phi1, relative humidity incoming air 55 degree, velocity of the incoming air 100 cube, and TB barometric pressure 1.03 and TD2 temperature of the outgoing air of the dry bulb temperature of the outgoing air 27 degrees centigrade. First, mark the initial condition of the air, that is 35 degree air temperature and 50 degree relative humidity of the psychrometric chart. How you do it? 35 degree relative 35 degree dry bulb temperature. This is the point we are finding. Make a vertical which will intersect at 55 degree percent relative humidity here. Same is here, 35. Make a draw a vertical, intersect at 55 degree relative humidity. From the psychrometric chart, so that dew point temperature at 0.1 is equal to 14.5. So what we got? A horizontal line intersecting from the 0.1 to the wet bulb temperature line is a dew point temperature line. It is TP1. Same is the case here. We make a vertical, will intersect here at TP1. We can from the sub line point intersection, we can calculate the dew point temperature at the 0.1. This temperature, saturation temperature at the partial vapor pressure of the incoming of the air at the incoming temperature. Means if we reduce this temperature from this a bit, it will just fall from this thing, moisture and the humid content will be reduced. Since the temperature of air leaving the coil, that is 27 degrees centigrade, which is given here 27 degrees centigrade, and or the effective temperature of the coil above the dew point above the dew point temperature of entering air is 24.5 degrees centigrade. There can be no humidification takes place. What is saying? The temperature leaving the coil is 27 degrees centigrade. The effective temperature of the coil is above the dew point temperature of the incoming entering air. Means there can be no humidification. Humidification dew point temperature of the air is 24 degrees centigrade. So the temperature of the air leaving it's above the leaving the air is more than the dew point temperature. So it cannot form any moisture, thus it cannot reduce the temperature and there is no humidification is possible. Thus, a sensible cooling factor process from 38 degree dry bulb temperature is a 55 dry bulb temperature, 35% relative humidity to 27 degree dry bulb temperature as shown in the line 1, 2 on the cyclometric chart. The point 2 represents the condition of air leaving the coil. Point 2 represents the condition of the air leaving the coil, which is higher than dew point temperature. As a result, there should not be any humidity friction. From the chart, it is clear that enthalpy of our entry at point 1, if we drop a particle from point 1 to the enthalpy line, is 85.4. The specific volume of air entering the coil per minute, if we drop from here to specific volume line, it will take 0.9 cubic per minute, cubic cube per minute. No enthalpy air leaving at point 2. H2, 77 kilojoule per kg of dry air. We know that the mass of air entering the coil is equal to the velocity of incoming air divided by specific volume. That 100 velocity is equal to 100 and 0.9 is specific volume for 1.1 kg per kg. So tons of refrigeration, the mass of air coming in multiplied by the enthalpy of the incoming air minus the outer air. So the triple 1.1, 85.4 minus 77 is 933.24 kJ per kg. So if you divide it by 250, that is 44.33 R. The final relative humidity on the submitted chart, it is clear that humidity of the air leaving the coil at point 2 is given. It is intersected the phi 2 at 86%, 86% phi 2 curve. The essence of refrigeration required, terms of refrigeration required is when surface temperature of cooling coil is 10 degrees centigrade. When bypass factor is 0.1. Since the surface temperature of the apparatus dew point is 10 degrees centigrade, of cooling coil is less than the dew point temperature of liquid entering the air. Therefore, there is a cooling and humidification process takes place. And at point 1, this ground level temperature and 51 degrees centigrade temperature to 0.3 in the since the surface temperature of apparatus dew point, that is 10 degrees centigrade of cooling coil, is less than the dew point temperature entering at 43 degrees centigrade. Therefore, it is a cooling and humidification process. Now, the point 1, 35% driver temperature 35 and 55 relativity of the to the point 1 of the high pressure car. That is ADB, 10 degrees centigrade. The mark point 2 of the slide A3, that is the point 2 here. This is the point 2 here, right here and right here of the pneumatic chart. That is the driver temperature at outlet air point 2. The bypass factor is TD2 minus TD here by TD1 minus ADP minus ADP. So put this value TD2, you don't know. And 35 minus 10 minus 10 equal to 0.1. 22 equal to 0.1, 25 plus 10 is 12.5. Now, draw a parallel vertical line from the TD2 12 degree to intersect the line 1, 3. This represents the final condition they are leaving the coil. They drop a particle, it will intersect line AB at point 2. From the psychrometric chart, we find the enthalpy of the air leaving the coil is 35 degree point kg. So tons of mass multiplied coming here and outlet difference with the outlet here, but 1.1 is 85.4 minus 35 minus this 56,000 kg per wind. From psychrometric chart, find that the specific air intensity coil at point 1 is given by this one. That at the outlet of the coil is given by this one. The continuous flow, they are condensing in the coil. F1, the mass of the air coming flowing in. F1 minus W1 W2 is equal to 1.2 kg per minute. Now let us start another portion of this section, cooling with adiabatic humidification. When air is passing through an insulated chamber, when there is no heat transfer takes place, then sprays of water known as air washer maintained on a temperature of T1 higher than the dew point temperature of air entering air. So sprays of water maintained at temperature T1, which has the dew point temperature. Dew point temperature is the temperature at which the moisture content in the air vapor and air mixture will start condensate according to the uh, partial pressure of the vapor inside this mixture. Now, if the water comes at a temperature higher than this temperature, there will be no such moisture takes place. But not at the type of temperature of entering air or equal to the cold wave temperature or to the corresponding at TW. Then atmosphere, then the air is said to be cooled and unified since no heat is supplied or rejected from spray water as the same. Then air is said to be cooled and unified since no heat supplied or rejected from spray water at the same water is recycled again and again. Therefore, in this case, condition of active expansion will be reached. The temperature of spray water will reach the automatic white part temperature of the entering air. The process in point 3, this effort chart will be given by the following is the path of the condenser as the explained for temperature or constant enthalpy line. This process shown what is being explained here. Just a second. So here we are discussing the adiabatic humidification. Now, the air passes through insulated chamber, means there should not be any heat transfer takes place. As in the figure. Here the air is coming in from the left side of the chamber and coming out to the right, and there is a spray nozzle where there is the water jet is being sprayed in the air, where it is being, after sprayed water is being calculated, recirculated to the bottom and draws by the again the pump, and again the spray takes place. Means there's this continuous process, the same water is being drawn and sprayed and again collected, again drawn and sprayed and collected. And if there is anything wastage of the water, as a portion of the water is being absorbed by the air and air out, so you have to supply, make up the water to a certain extent. And this whole setup is supposed to be insulated. So there should not be any temperature takes place, temperature heat transfer takes place. Now, the sprays of water maintain the temperature higher than the dew point temperature of the air. Say air has a partial pressure, and as per this partial pressure, it has a dew point temperature, which means it's saturated temperature, which after which the temperature is reduced, then there will be the condensation of the moisture inside, kept inside the air vapor air mixture will take place. Now, if the air sprays of water, with the water spray maintain the temperature higher than dew point temperature, then but lower than the dry bulb temperature of air entering air or equal to the wet bulb temperature of the entering air, then the air is said to be cool and liquefied. Means air is fully saturated and its temperature is equal to it, and the air is coming in the dry bulb temperature, coming lower than the dry bulb temperature and equal to the wet bulb temperature, which means it's fully saturated and cool and modified. Since no Since no heat is supplied or rejected from the spray water, as the water heat from the spray water, as the wave water is separated again and again, therefore in this case, a conditional adiabatic saturation will be reached. Means there is no heat transfer takes place, but the air is fully saturated with air vapor. The temperature of spray water will reach thermodynamic wet bulb temperature of the air entering the spray water. This process is shown in the light one in the psychrometric chart. 1 to 3 line means the line here, line number 1 starting from this point, and line number 3 ending this point. In an ideal case, when the humidification is perfect of the humidified efficiency of the spray temperature is 100 degrees centigrade. And it follows the path along the constant vapor temperature line or constant enthalpy line. In an ideal case, when the humidification is perfect or the humidified efficiency of the spray temperature 100 degrees centigrade, then final condition of the air will be at point 3. That is temperature 23 and humidity 100 degrees centigrade. In actual practice, the perfect humidification is never achieved. When the humidity perfect means humidified efficiency of the spray temperature 100%, means spray chamber can be humidified 100%. With final condition will be at 3.3. Temperature at 23 and humidity 100%, but its nature achieved. Therefore, the final condition of the air at outlet is represented 0.2 in the line 1, 3. The point 2, which is shown here, this is here. They are also obtained by dividing the line 1, 3. In following way, line 2 to 3. Hereby line 1 to 3 is going to bypass factor of the point 1. The effectiveness or amplified efficiency of the spray chamber is given by efficiency of the humidification or humidified efficiency, actual drop in type of temperature, and ideal drop in type of temperature. Actual drop is specific humidity, means actual drop is of the moisture present per kg of the mixture, and ideal drop in the amount of moisture present per kg of the mixture. So TD1 minus TD2 divided by TD1 plus TD3 is equal to W2 minus W1 divided by W3 minus W1. When the sprays of water are maintained at a temperature lower than the wet bulb temperature, sprays of water that is maintained at a temperature